Bonding in complex ion, strong field ligand will cause the d electron to be paired up. So for the weak field ligand will not cause the d electron to be paired up. So this is the weak ligands and this is the example of the strong ligands. So this is the example of the strong ligands and this is the weak ligand. We look at the example, valence bond theory, sp3 outer shell hybridization. So this is the outer shell hybridization. So for the 4 coordinate compounds, tetrahedral complexes. So this is the example. So this is the tetrachloro. So this is the cobalt. So because this is the negative, so it become the cobaltate. So how many the oxidation number of metal for the cobalt? So cobalt here is positive 2. So the name is tetrachlorocobaltate 2 ion. So this is the electron configuration. Cobalt here. So this is the cobalt 2 positive. So this is the electron configuration. And this is the orbital diagram. So we know this cobalt 2 positive because 2 positive here. So that's why here is positive 2. And since for the chlorine is a weak field ligand, so 3d electrons are not paired up. So we need to know which one is the weak and also the strong field ligand. So you need to memorize these trends. So this is the Cl. So Cl here is the weak field ligand. So because this is the 3d7, so you fill up here is the 7 electron. So 1, 2, 3, 4, 5, 6, 7. And then we look at the ligands. So because of the ligand here is the weak field ligand for the chlorine, so you need to not pair up of the electron. So meaning that the weak field ligand is the paramagnetic compared to the strong field ligand is tend to be diamagnetic. So since there are 4 ligands around the central metal atom, so meaning that this is the sp3 because 1, 2, 3 orbital. So the hybridization is the sp3. So this one we call as the outer shell hybridization. If the outer shell, so meaning that out from the d orbitals. So after 3d is the 4s and 4p. So we look at the dsp2 for the inner shell hybridization. So if inner shell, so meaning that we know this is the include of the d orbitals. Okay, now we look at the 4 coordinate compounds. So this is the nickel. So this one cyano. So cyanide ion. So we know here is the -1 for the oxidation number. So we get here is the +2 of the oxidation number of nickel. So the name is tetracyano nickelate 2 ion because this is the ion. Electron configuration. So nickel here 28, and this is the positive 2, so meaning that 26. So we have the 3D 8 because we remove the 4s2 electron from here. So now, because of the Cn is the strong field ligand, so strong field ligand tends to form a diamagnetic. So meaning that pairing of unpaired 3D electron. So we have the 8 here. So meaning that this one need to pair of electron. So 1 goes here and another one space, empty space here for the hybridization. So 1, 2, 3, 4. So DsP2, only 2 orbitals of the P. So this is the hybridization. DsP2. So we look at the sp3d2 for the outer shell hybridization. So this is the 6 coordinate compounds, meaning that the octahedral complexes. So this is the geometry of the complexes. So consider here is the compound. This one hexa-aqua. So for the iron, the oxidation number is positive 3. So we do the electron configuration. So the first one, find the oxidation. Second, electron configuration. And the third one, draw the orbital diagram. So we take here for the Fe, 3 positive. So now 3d5. So this is the 3d5. So look at the water. So water is a weak field ligand. 3D electrons. So because this is also the outer, don't disturb the 3D. So meaning that only the outer shell hybridization, outer from the 3D orbitals. So we have the 6 coordinate compounds. So 1s, 3p, and they have the 2 orbitals of the 4d. So now the hybridization is sp3d2. Because of 3 orbitals of the 4p, and this is the hybridization. So now we look at the D2sp3 of the inner shell hybridization. So still 6 coordinate compounds, octahedral for the complexes, for the geometry, and this is the example of the complex ion. So here oxidation number of metal, nickel positive 3, and this is the, sorry, it's not the nickel. So this is the iron, positive 3, and this is the electron configuration of the iron 3 positive. And here, look at the ligands. Ligands is a strong field ligands, and it causes the pairing of unpaired 3D electron, so meaning that they are magnetic. So now, pair all these electron. So because of 5 here, only 2 pair and 1 left here. And then you must have the space of the D2 for the empty space, D2 sp3. So this is the inner shell hybridization. So the hybridization is the D2sp3. Crystal field theory explains that the bonding on complex ion purely in terms of electrostatic force. 2 types of electrostatic interaction involve: 1. Attraction between the positive metal ion and negatively charged ligands. Second one is electrostatic repulsion between the lone pair on the ligands and the electron in the d orbitals of the metals. This is the crystal field theory for the octahedral. central metal atom surrounded by 6 electron lone pair. We call it as the ligands. So all 5 d orbitals experience electrostatic repulsion. The magnitude of repulsion depends on the orientation of the orbital involved. So this orbital, the lobes point toward where the lone pair located, thus it will experience greater lone pair d orbital electron repulsion. They will be higher in energy, thus 5d orbitals are split between 2 sets of energy level. So the T2G set of orbitals lower in energy and EG set of orbitals higher in energy. So this is the splitting energy. You have the potential energy for the d orbitals, and this is the crystal field splitting. So this is the EG and this one T2G. So you just remember EG 1, 2, so 1, 2 here. T2G have 3, so 1, 2, 3. So this is the lower energy and this is the higher energy. So this one is energy difference between 2 sets of d orbitals in a metal atom when ligands are present, has direct effect on color and magnetic properties of complex ion. This is the crystal field theory tetrahedral. Central metal atom surrounded by 4 electron lone pair, which is the ligands. The d orbitals of tetrahedral complexes also split into 2 groups. So the dxy, dyz, and dxz orbital points in the direction of the ligands. They will be higher in energy than the degenerate orbitals of the free metal atom or ion. So the dz squared and dx squared minus y squared orbitals point between the ligand stars are lower in energy. Thus 5d orbitals are split between 2 sets of energy level. T2G set of orbitals higher in energy and EG set of orbitals lower in energy. So this is the crystal field theory of the tetrahedral. So this actually T2G and this one is the EG. Let's have 1, 2. So this one 1, 2, 3. So difference with the octahedral is 2, 3. And for the tetrahedral, 3, 2. The crystal field theory for the square planar. There are 4 ligands as well. The difference is that the electrons of the ligand are only attracted to the plane. There are 4 different energy levels for the square planar. So this is the high energy and this is the lower energy. 1, 1, 1, 2. This is the tips of the crystal field theory.